Okie doke. Welcome back to 3.2 exponential functions and their graphs. Here we're going to be recognizing and evaluating log functions with base A. We're going to be graphing log functions with the base A. We're also going to deal with natural logarithmic functions. So hopefully you guys enjoyed today, because you actually may use it somewhere in real life, somewhere down the road. So let's move on to example 1. Or actually, let's figure out what a log function is in the first place. Back in the good old days of section 1.6, we learned about inverse functions, and here in 3.2 they're going to come back into effect, because in 3.1 we learned about exponential functions. Well, they have inverses because they are one-to-one, and the graphs of those can be reflected over a specific line. So if we have our graph of an exponential function, okay, here's our x-axis, here's our y-axis, and say you have your exponential function which goes along your x-axis, goes up through y equals 1. Well, this is one-to-one. It passes your vertical line test, but it's one-to-one because it passes your horizontal line test, which means it must have an inverse which is reflected over this line right here, this y equals x. And since you have an inverse over this line, then that means you're going to get a graph that is going up through here and ends up looking like this, and this ends up going through x equals 1. This is a logarithmic function, and I'll shorten it log function. Over here, the green one, this is your exponential function. So exponentials and log functions are inverses of each other. The way you write a logarithmic function is y equals log base a of x, and your a is your base. Okay, you can rewrite this by taking this a over and bumping up this y, so you can turn it into an exponential function. And what that does is that cancels out this log, so you're left with only an x on one side, and then you get an a to the power of y. So that is your possibility for when you're trying to convert logs into exponential functions. They are inverses. So the first thing we want to do is evaluate some log functions. What a logarithm really is an exponent. Okay, it is the exponent that you raise a base to equal some power. So if you look back here to where we just were, this y value, okay, if you evaluate log base a of x, you're evaluating that and you're getting some number. Well, this number, this y value here, is the exponent that you raise a to, your base, because a is your base, you raise a to equal whatever x is. So when we look at our example 1 over here, actually even before that, if we have log base 2 of x, and that is going to be equal to that's going to be equal to 4. Or sorry. Let me goof that one up here a little bit. Log base 2 of 8, and that's equal to y. Well, what y is, that is the exponent to which this 2 is raised to equal whatever 8 is. So in this case, y is equal to 3. And you're like, well, how in the world does that work? Well, if you take this 2, bring it over and bump up this y, that's going to give you 2 to the power of y is equal to 8, because your logs just cancel. So what that means is y is equal to 3 because 2 to the third power is 8. So y equals 3, your answer to a log problem, this is always an exponent. Okay, that is your answer, is what you're finding is an exponent. You're not finding a base, you're not finding like a coefficient or something like that, you're finding an exponent. So when we look at example 1 here, if we can do this without a calculator, believe it or not. If you want to solve this, you want to find out what f of x is when you have the log base 4 of 16. So f of x is going to end up, that is the exponent to which you would raise 4 to equal 16. Well, we know that 4 squared is 16, so your f of x, or your y, is just equal to 2. Same thing here on b. If we have f of x equals the log base 2 of 64, then we have to figure out, well, what is the exponent that we can raise 2 to get a 64? Well, if you take 2 times 2, that's 4, so there's 2's. 2 to the third power is 8, 2 to the fourth is 16, 2 to the fifth is 32, 2 to the sixth is 64. So your exponent that you'd raise 2 to equal would be 6 to get a 64. Now if you plug in f of x is equal to, or log base 5 of 1, and that's what f of x is equal to, then you'll notice something kind of peculiar. Well, we want to figure out what can we raise 5 to equal 1. Well, it might be easier if you rewrite this as f of x instead of an f of x, make this a y. And if you do your little change of base, or not change of base, if you write it as a base form, so this 5 comes over and bumps up the y, and you're going to end up and get 5 to the power y equals 1. Well, the only thing that you can get, or that you can take a number to, a power, and get 1, that is 0. So in this case, your y would be equal to 0. So that means anytime you take a log, no matter what your base is, and if this x value is a 1, then your function is going to be evaluated at 0, because the only time you can ever get a 1 whenever you evaluate a log is if your exponent is going to be a 0. And that doesn't matter if this is a log base 6 of x, or log base 6 of 1, log base 7 of 1, log base 10 of 1, whatever. It's always going to be equal to 0. Now d is a little bit tougher, because you have to think on this one. That's always a bummer. And you get f of x equals log base 3 of 1 over 81. Well, the best thing to do here is you can rewrite this log base 3 of 81. 81 is a power of 3. So if we write this as log base 3 of 1 over 3 to the 4th, which we don't want this as written as a fraction. We're going to write this as log base 3 of 3 to the negative 4, because if we just move this 3 to the 4th up to the top, that just turns out to a negative. So what happens here is your log base 3 and your 3 just cancel out. In your answer, you end up getting a negative value, a negative 4. So that should tell you anytime your base is a whole number and your x value is a fraction, then your solution is going to end up being negative. So that's another little quick reminder there. And these are all things, you know, because I've done logarithms quite a bit in my head, I get them, I kind of know what I'm doing here. So if on the last one, if it helps you to write this instead of f of x as y equals log base 3 of 1 over 81, and then you have to turn it into an exponential function, which might be a little bit easier for you to understand. This 3 comes over and bumps up the y, so you get 3 to the power of y equals a 1 over 81, which you can write that 1 over 81, oops, don't know that happened, which is a 3 to the negative 4. And if you notice, your two bases are the same. If those are both 3's, then that must mean that y is equal to negative 4. So that's another way you can look at it. And that's probably how you learned it in Algebra 2. Either way, you get the same solution. So I hope you remember some of the stuff about logarithms. A little intro here on evaluating logarithms. Logarithms are one of my favorite things to go through the year. It's just kind of fun, a little different. So I hope you remember how to evaluate them.